Hello and welcome to a brief demonstration on graphing rational functions used from their algebraic formulas. This slide shows purpose is to demonstrate how to obtain a graph of a rational function from an algebraic description. Some materials for review include finding the domains of rational functions. This is accomplished by setting the denominator equal to 0 and solving. We shall also want to determine intercepts of rational functions. X-intercepts are found by setting the numerator polynomial equal to 0 and solving. Double check to make sure the value is in the domain. Y-intercepts are found by substituting x equals 0 into the rational function and simplifying. And again, double check to make sure 0 is in the domain. Another thing we're going to want to find are the asymptotes of rational functions. This refers to all types of asymptotes, the vertical, the horizontal, and the oblique asymptotes. Vertical asymptotes make the denominator 0, but not the numerator. Horizontal asymptotes occur when the degree of the denominator is greater than or equal to the degree of the numerator. If the degree of the denominator is greater, then y equals 0 is the horizontal asymptote. If the degrees are equal, then the ratio of leading coefficients is the horizontal asymptote. Oblique asymptotes occur when the degree of the numerator is greater than the degree of the denominator, and these are found by performing division. And consider the quotient. The remainder will have a degree strictly less than the denominator via the division algorithm. And another thing we're going to want to determine before we sketch the graphs of these things are holes in rational functions if they are present. Holes occur when the root of the denominator is also a root of the numerator. This leads to a 0 divided by 0 form, which is indeterminate and not undefined. And indeterminate means that we need to have further investigation, and these steps are listed here. So we're going to reduce the rational function by canceling the duplicated factor. Then we're going to substitute the x value into the reduced form. This x value is the same value that made both the numerator and denominator equal to 0 in the original rational function. When you do this substitution into the reduced form, if a numerical value occurs, then you have a hole. The x-coordinate is the value that makes the denominator and numerator equal to 0 in the original rational function. The y-coordinate is the value that results when using this same x value in the reduced form of the rational function. Some additional notes on the examples here. The generic symbols used in this presentation when needed are r of x for rational function, n of x for numerator polynomial, d of x for denominator polynomial, and r bar of x for the reduced form of the rational function. And these are capital letters. If you have trouble remembering the conditions for horizontal asymptotes or oblique asymptotes, go ahead and perform division on the rational function. The quotient is the horizontal or the oblique asymptote. The guidelines for finding horizontal and oblique asymptotes are merely shortcuts that avoid this division. So you may consider the horizontal asymptote as this very, very special case of the oblique asymptote. Now, complex solutions of any kind are not considered here as part of the graph. And this is because we're graphing in the real plane. If a complex number is required to make either the numerator or denominator equal to 0, we go ahead and discard it here. So in this example, we're going to determine the graph for the rational function r of x equal to 4x cubed plus 12x squared minus 16, and all of that's going to be divided by the polynomial x squared minus 3x plus 2. First, we're going to have to factor the numerator and the denominator, and we begin with the numerator. Now the details here show that we can rewrite 4x cubed plus 12x squared minus 16 as 4 times the quantity x plus 2 squared times the quantity x minus 1. Now we're going to go ahead and factor the denominator as well. X squared minus 3x plus 2 may be rewritten as x minus 2 times x minus 1. Now that the numerator and denominator are factored, we go ahead and follow our procedure. We're going to identify the domain. Now the domain is all the values that do not make the denominator 0. If it makes the denominator 0, we don't want to include it in the domain. So here, when I have the denominator factored, I can see that x cannot be equal to 1 and x cannot be equal to 2. If it does equal one of those values, then I have a division by 0, which is illegal. Now the graph is going to approach positive or negative infinity when x is close to 2. And this implies that x equals 2 is a vertical asymptote. The vertical asymptote at x equal 2 will have a factor of x minus 2. And we see this in the factorization. Now this root has an odd multiplicity. So there's going to be a change in sign as we read left to right across this root. But in this case, we also have a hole in the graph at x equal 1. Since we wrote the numerator and denominator in their factored forms, we can see that x minus 1 is a factor of both the numerator and denominator. So the domain of the original rational function cannot include 1, because that forces a division by 0. But when I try to put 1 into the original rational function, I end up with a 0 divided by 0, which is indeterminate. That means I have to investigate further. And according to our steps, we're going to reduce this rational function. So I cancel off the x minus 1 factor from both the top and the bottom, and I end up with 4 times the quantity x plus 2 squared divided by x minus 2. Now I go ahead and substitute x equal 1 into the reduced form, and that gives me a value of negative 36. This means that there's a hole in the graph at 1, negative 36. So let's see what our information tells us right now. So as of this moment, what we have discovered is that we have a vertical asymptote at x equal 2. Now I draw this with a dashed line. In this case, I use the color red. But a dashed line means that it's not a part of the graph. Okay? So here I have this dashed line at x equal 2. That tells me that's a vertical asymptote. I also have an open circle drawn at the location 1, negative 36, because that's where the hole in the graph is. Now, continuing with the analysis, we see that the numerator had a higher degree than the denominator. And the good news is that at this point, I can use the reduced form to complete the analysis. I do not have to go back to the original form. So the degree of the top was 2. The degree of the bottom is 1. That means I have to do long division to find this oblique asymptote. So when we do the division, we can see the details of long division here. We end up with a quotient of 4x plus 24. That's going to be the oblique asymptote. And what this means is that as I get further away from the origin, I will get closer to this line, 4x plus 24. The remainder is 64. And because 64 will never equal 0, I can see from this result that my rational function will not hit this oblique asymptote. So let's see what the graph, or what this information tells us about the graph now. So up here in blue, we have graphed this oblique asymptote 4x plus 24. And we can get an idea about what our rational function is going to look like. And we don't have all the information yet, but we will, that we need in order to sketch a graph of this thing. So for right now, we have our oblique asymptote as this slanted line, or just, this line here. So a slanted asymptote is a special case of the oblique asymptote, meaning that it's just a linear function that the rational function will get close to as I get further away from the origin. Now we may determine the intercepts. And again, we can use the reduced form here. The x-intercepts are where the numerator is equal to 0. And when I set the top equal to 0 and solve, I get x equal -2. But this has a multiplicity of 2. So the only x-intercept is going to be located at -2, 0. It has a multiplicity of 2, which means the graph is going to bounce off the x-axis at this point. This again comes from the definition of multiplicity of roots from polynomial theory. So this is us using those ideas from polynomials to help us sketch the graph of this rational function. The y-intercept is accomplished when you plug 0 into the rational function. So at this point, we can go ahead and say when I put 0 in, I get -8 back. So the y-intercept is going to be located at 0, -8. So let's take a look at the graph and put this information in as well. So now that I have all my asymptotes, my holes, and my intercepts plotted, along with knowing the multiplicity of the roots to the bottom and the roots to the top, then I can go through and start sketching the graph. Okay, so what we're going to do here is we're going to connect -2, 0 and 0, -8. We're going to start by connecting these 2 points because we know that rational functions are continuous over their domains. So that means that I should be able to connect those 2 points with no breaks or holes or whatever. Now, as I continue to go through the y-intercept, I have to get to the hole in the graph. So I'm going to go ahead and connect this intercept with the hole. And this asymptote here at x equals 2, because it's a vertical asymptote, tells me that I have to either get close to positive infinity or negative infinity as I get closer to x equals 2. Well, I can't go off to positive infinity because I would have to cross the x-axis, and that would imply that there's a solution. But we already know there's no solution because we found them all. So we have to go toward negative infinity. So from this hole, I'm going to continue to draw my graph toward negative infinity as I get closer to this vertical asymptote x equals 2. Now I know that x equals 2 was a root of odd multiplicity in the denominator. That means that there's a change in sign as I go to the other side of the vertical asymptote. So because it was negative down here, on the left side of the vertical asymptote, it's got to be positive on the right side. But I also know that when I'm close to x equals 2, I should be very close to infinity. I should become unbounded. So I know that as I get close to x equals 2, my graph is going to get closer to infinity, positive infinity. So we have this little piece here. Now, as I go further away from the origin, I'm going to get closer to this oblique asymptote. And I know I do not intersect the oblique asymptote because the remainder was a constant. So I know that as I go further and further away from the origin, I'm going to get closer and closer to that oblique asymptote. So it's going to look something like that. And right now, this is what I have. I have about half the graph already. And again, I'm just using these ideas of the definitions of the asymptotes and the ideas of multiplicities of roots and just applying those thoughts to help me sketch this graph. Now back to our x-intercept here at -2, 0, we discovered that that particular root was of even multiplicity. Because it's of even multiplicity, that means it's going to bounce off the x-axis. It's not going to change sign. So from this x-intercept, I'm going to go ahead and bounce off the axis. And I'm going to have a graph that kind of does this. Now I know that as I go further away from the origin, by definition of oblique asymptote, I'm going to get closer to that line 4x plus 24. So I'm going to take my graph piece right here, and I'm just going to continue it on until I get closer to that oblique asymptote. So this is essentially what my sketch is going to look like. And when I go to technology to give a more accurate graph, it should look something like this, because again, I'm just using the definitions and using those ideas from polynomials. So let's take a look and see what the technology shows us. Here is a graph of the rational function using technology. And here we can see that our graph here in blue and our sketch drawn here looks very similar. So our sketch coincides with the technology, or you could say the technology coincides with our sketch. But in this case, we see that using the ideas and definitions from polynomials and for asymptotes, we were able to get a pretty good representation of this rational function. Thank you for your time and attention.